We have a face-centered cubic unit cell, and I wanted to discuss HKL lattice planes. And I have in this face-centered cubic unit cell model, I have this sort of shaded piece of plastic here representing a lattice plane. And we want to describe its orientation. We're going to select this point as the origin. We're going to call this the A-axis, the B-axis, and the C-axis. And so to describe that plane's orientation, we need to figure out how it intersects these axes. So this plane intersects the A-axis at one full unit cell length away. So we could describe A as 1. This plane never intersects the B-axis. This edge here runs parallel to the B-axis but never intersects it. And so we can think about B in this case as having an intersection point of infinity because it never really does intersect that axis. For the C-axis, this plane intersects the C-axis about half of one unit cell height. Okay, so C would be 1/2. Again, intersects 1/2 of the height of the unit cell. And so to convert these to HKL designations, we take the reciprocals of these numbers. And so H would be, reciprocal of 1 is 1. The reciprocal of infinity for K is 0. And C will convert to L, and the reciprocal of 1/2 is going to be 2. So the HKL designation for this plane here would be 1, 0, 2, like that. And there are other planes in this unit cell, but I should also mention directions. Okay, directions are set from the origin, and they intersect the planes. For a cubic unit cell, fortunately, the direction is perpendicular to the planes of the cubic unit cell. So if I use this marker to represent a direction, it would be pretty much like this. It would go through the origin and run perpendicular to that plane. Okay? And we can show other planes in this unit cell. And remember, there are equivalent sets of planes with different directions here. But a couple other planes we could indicate here. And again, we might have to move around our origins to show this. But this triangle here designates a plane, and this sort of plane that kind of runs from edge to edge could be described as sets of 1, 1, 0 planes. And another set of planes we can describe are planes that connect the corners here. You can see this plane described by these red spheres here, or by the gray spheres here. These would be described as 1, 1, 1 planes in this face-centered cubic unit cell. So there are all sorts of different planes. One last thing I want to mention with respect to geometries associated with this cell, and I'm going to flip this back around, is this triangle also shows some of the dimensions through that unit cell. Okay, if we are describing in this unit cell this length A, and it's a cube, so A is really mathematically the same as B and C with respect to length. This diagonal here that goes across the face from one corner to the other is going to be root 2A in length, because it's really, figure out this length, it would be a 45, 45, 90 right triangle, okay? And if this is A and this is root 2A along this length, then the body diagonal, the diagonal that goes from opposite corner to opposite corner through the middle of the cube, is going to be root 3A. And again, that comes out of the geometries associated with right triangles. So there's all sorts of information we can unpack using this model.